the last one.
That was very nice.
Yeah.
Very good discipleship and that was
All right, well, today we are going to do Chapter 11. Just had a discussion about Chapter 10. Chapter 10 is equilibrium. You will be happy that we skipped it. Equilibrium is general chemistry fodder, and it's somewhat difficult. It's also Veterans Day, so happy Veterans Day if any of you are. I was in the Army in 1969, a very bad time to be in the Army, but I'm here.
yes.
So, Chapter 11 is radioactivity. When we speak of radioactivity, most people think of power plants and bombs. Well, sometimes they're both. This is Fukushima in Japan. In 2006, the nuclear power plant here was hit with an earthquake and a tidal wave. Huge clouds of radioactive smoke, very bad disaster. It's still a hot spot. We'll talk about it a little bit later. If you note, all around the power plant, because it's Japan, it's very congested. There are places that have little farms, little gardens and stuff like that. When the radioactivity subsided enough, people went back, even though they shouldn't have. Kind of like a two-for corn. These are tomatoes. It really did a job on things in the area, very high radioactive things. My favorite, of course, though, is the shark-seagull hybrid. Okay, it's Photoshop, but the others are real. The others are real. Just a reminder, on Wednesday we're doing Chapter 12. That's an intro to organic chemistry, and we're going to do that in the lab room D204. Quiz 2 will be live on Blackboard as soon as I finish talking today. Following Monday, we will have Exam 2 review back here. So make sure you print. Make sure you print the sample exam, work one, hand it in, save the other for notes, just like last time. Exam number 2 is on Wednesday. Again, we will do this in 204. Any questions? All right, well, radioactivity is kind of a fun chapter. We'll talk about how to make bombs, stuff like that. It'll be fun. It's good stuff. Going way back, long time ago, we said that the atomic number of an element was the number of protons in its nucleus, and this is what defines which element you're dealing with. We used a tool called the atomic symbol, where we took the symbol of the element, put the mass number and the atomic number on it. The mass number goes in as a superscript, and the atomic number goes in as a subscript. One of the examples we looked at was carbon. Carbon exists as carbon 12, 13, and 14. These are the three atomic symbols. Again, they're all carbon. They just have different masses. Carbon 14 is the radioactive version. We'll talk about how we can use this, carbon 14, for radioactive dating. Well, radioactivity was discovered right around the turn of the century by a French group that was working on phosphorescence. Basically, it was an accident. They used photographic plates in their phosphorescent work. Somebody went in and put a jar containing uranium salt on the plate in a dark room. And then when they went to develop a thing, it had these big splotches all over it. The guy was probably fired because plates in those days were a real pain to make. You had to make them by hand. You couldn't buy them at CVS, whatever. You had to make them by hand. They were some emulsions sandwiched between glass. Had to keep it very dark, blah, blah, blah. Nonetheless, we're in this experiment. So, people generally wanted to know what was happening. The result came from the work of Curie and others. Turns out that the uranium salts were emitting subatomic particles. There were three that Curie and her group identified. Alpha particle. Alpha particle contains 2 protons, 2 neutrons, no electrons, and it has a charge of +2. It basically is a nucleus from a helium atom with no electrons. A beta particle was another one that was produced. Beta particle acts as if it's an electron, but by George, it's coming out of the nucleus. That was very puzzling, exactly how that could happen, but beta particle really acts like a real electron. Gamma. Gamma was the most energetic. It was neutral, no charge, and it acts as if it's a very high energy photon, so a ray of light, like an X-ray except super high energy. We are constantly bombarded by gamma particles. I have a little Geiger counter here we'll see in a minute. When I turn it on, we'll get an occasional click from interstellar space. Very energetic. Alpha particle is the least energetic. It is fat, it is heavy. You can stop an alpha particle with a sheet of paper. This represents a centimeter of lead. Most beta particles will be stopped by a centimeter of lead. Gamma, this is supposed to be 10 centimeters of lead, and some of those can just zip right through, just like it's nothing. There really can be high energy. The way we measure radioactivity, simply anyway, is to use a Geiger counter. Now this is a 1950s version of a civil defense Geiger counter. The idea was they had these things everywhere. When the bombs fell, people would take these out and go and see where all the radioactivity was. Not a good thing to do anyway, but. So this is a Geiger counter. You have a little wand here, and you look at a gauge, and the thing goes click. The way it works is something like this. You have a power source, you have a counting mechanism of some sort, and you have a tube, a little Geiger tube it's called. The tube has a central probe that's insulated from the outside, anode, cathode, so they're charged. Okay? Basically, you fill it with a little bit of, tiny bit, of something like krypton, neon, a gas, usually an inert gas. When a particle of ionizing radiation comes in, what happens is you get a small lightning bolt from the ionizing radiation from here to there. The electronics converts that into a click. Well, I just happen to have my very own little Geiger counter here. Let's see if there's any gamma rays. Well, there were a couple. Another one. Another one. Okay. Yeah, so this is a cute little Geiger counter. This is uranyl nitrate. uranyl nitrate has a uranium in it. This is actually, quote, depleted. So what they have done is they have taken the fissile isotope out of this, and this is the leftovers. Depleted uranium is very hard as a metal, very dense, very, very heavy. It's used in armor-piercing shells. So you make shells out of this stuff, it'll zip right through a tank. So, this is, supposedly not radioactive. Beautiful little yellow powder. Another gamma ray or two. It's kind of neat. This is so much fun. Every one of those clicks is a uranium atom decomposing and emitting a particle. What about radon? What about radon? We'll actually talk about radon in just a minute. So this is the high point of my lecture. I get to play with my Geiger counter. All right. So let's see where these particles come from. They come from the nucleus. Alpha particle is probably the easiest one to understand. Here we have a pretend atom, 12 protons, 12 neutrons. This just represents the nucleus. Alpha particle is 2 of the protons, 2 neutrons, mass number of 4. Again, this is equivalent to a helium nucleus. And basically what happens is that 2 protons, 2 neutrons get tired of living in the center of this atom. Usually it's because it's big and crowded, and it just breaks loose. Here is your alpha particle. Now, we started off with 12 and 12. We have lost 2 protons, 2 neutrons. That means that the element that's left here, the atomic number, has decreased by 2. So now we have a different element. An example, this is the uranium that we just did. Uranium-238 has 92 protons in its nucleus. It's going to lose the helium nucleus, which is the alpha particle. Typically this is written as He42, and it's just understood that it has no electrons. The particle or the substance that is formed when this happens, we have lost 2 protons, so the atomic number will be 90. Look at our periodic table. We started here with uranium at 92. We're down to thorium at 90. We have lost 4 mass units. We started at 238. We are now at 234. So we have converted our uranium into thorium-234. This is called a nuclear equation. Sometimes the alpha particle is shown as a Greek letter alpha. Typically, though, it's usually He. Again, this is a nuclear equation. Let's go ahead and write one. Oh, let me just say, though, we have our little arrow here, right? For a standard chemical equation, we must have the same number and type of atoms. Well, we don't in this, but the mass numbers on this side must add up to that. The atomic numbers on this side must add up to that. All right. Thorium-230, we just made it. It also undergoes loss of an alpha particle. Let's write the nuclear equation. We will start with thorium-230. Thorium is here. It has 90 protons in its nucleus. So this is thorium-230, 90 protons. It's going to lose its alpha particle. When it does, the number of protons in the nucleus will drop from 90 by 2 down to 88. So we look here at our periodic table now to see what we got. The thorium is in the actinides, so it's here. 88 is radium. Our mass number started at 230, we lost 4. We're at radium 226. Nice, straightforward, and simple. Any questions? Do it again for polonium-214. Polonium is here, 84 protons in its nucleus. Well, we're going to start with polonium. 214, 84 protons. It's going to lose its alpha particle. That means the atomic number drops from 84 down to 82. So we look at our periodic table and see who 82 is. It's lead. We have gone from polonium to lead. We started at 214 plus 4 mass units. We're at 210. Any questions? Nuclear equations are simple. Once again, add up the mass numbers on both sides. They must be the same. The atomic numbers on both sides must add up. All right, that's alpha particles. Beta particle is a little strange. I said, what in the world is an electron doing in the nucleus? Well, it's not really there as an electron. It starts off life as a neutron. The neutron sheds its negative charge in the form of an electron, and when it does that, it's left as a proton. So we are converting a neutron to a proton and an electron. It's really nice, or would be nice, to think, gee, this is neutral, that's plus, that's minus. These are just stuck together to make a neutron. They're not quite that way. But nonetheless, neutron generates the electron. We're starting off again with 12 protons, 12 neutrons. One of these neutrons is going to convert itself into a proton. When it does, it emits the beta particle. Now, we started off with 12 protons in this nucleus. We now have 13. So the atomic number has gone up by 1. Thorium again, 234. Also loses a beta particle. When it does that, the atomic number is going to go up by 1. So we're at 91. There is thorium. We go up to 91. It's praseodymium, I believe. PA, not Pennsylvania. Now, the electron that's produced has no mass, negligible mass. Therefore, this is going to have the same mass number as what we started with. The symbol for the beta particle, we're going to use the Greek symbol beta, 0 for the mass number. Now, in order to make atomic numbers line up on both sides, this is 91, that's 90, this must be minus 1. And this is the symbol for the beta particle. Mass number is 0, atomic number minus 1. Okay. Bismuth 210, this is the beta. Write the nuclear equation. Bismuth 210, 83 protons in its nucleus. It is going to lose the beta particle. When it does, the atomic number will increase by 1. So we're starting here at bismuth. That's going to be, we're going to go to 84. That's polonium. Steel. The mass number doesn't change. This is polonium 210. Polonium 210 is a remarkable element. First of all, it is very, very, very toxic. Oh, about half a microgram will kill you within 2 weeks. Extremely toxic. It does it by emitting its own alpha particle. Atomic number drops by 2, mass number by 4. We're going to get 82 on this side, 82. We're back to lead. Going to drop this from 210 down to 206. This alpha particle, however, for an alpha particle, is extremely energetic. Extremely energetic. If you inhale polonium-210, even though alpha particles are really fragile, if you inhale this, it will get in your lungs. It will just eat your lungs out in no time at all. If you ingest it, it takes a little bit more, maybe a tenth of a microgram more to kill you, but is just as effective. This is the KGB's favorite assassination method. This is a Russian spy who was in England 1976, I believe. I don't remember his name, but he's dead. The Russians came. They didn't like him as a spy anymore. Invited him to tea. Just a fragment of whatever. Russia is the only country in the world that makes polonium-210. We actually buy it from them. Yeah, we buy about 8 grams a year. 8 grams of polonium is enough to kill everybody in the country. Everybody. And we buy that every year. I'm not sure what they use it for. But, sorry.
That makes nerve gases like nothing.
Light elements can also be radioactive. This is neon 19, so neon here, atomic number 10. It loses a beta. So let's do this one. Neon 19, going to lose a beta particle. That means the atomic number will increase by 1. If you go here at 10, down here at 11, is sodium. So we just made sodium 19. Any questions? Well, we have one more of the classic particles to do, and that's the gamma. Remember, it's just a very high energy photon, like a super X-ray or something. It is supposedly arise from an unsettled nucleus. So if you do something to get your nucleus real excited, oh, I don't know, heat it, whatever, it absorbs energy. When it absorbs energy, it is an excited state, and it dances around, and it loses that energy as this high energy gamma ray. We're not going to talk too much about gammas because they're neutral. They basically have no mass. Let's just look at a series here. Let's go ahead and complete these equations. Radium is going to lose an alpha particle. Radium is what killed Curie, if you know, a fairly toxic particle. So radium lives right here. It's going to lose 2 protons. When it does that, it's going to drop back here to 86. And it's going to be radon. The mass number will drop from 2226 to 222. The atomic number down to 86. Fluorine, another light element that's radioactive. Fluorine 39 loses a beta particle. When it does, it will start here at 17. The atomic number will go up by 1. So this is going to be argon. The mass number will not change, so it will be argon 39. Lead can also lose a beta particle, lead 214. When it does, the atomic number of the new element will increase by 1 to 83. 83, we're starting here at lead. 83 is bismuth. Mass number will not change, so it will be bismuth 214. And finally, radon 222 is an alpha emitter. When it does, radon is here at 86. The atomic number will drop by 2 down to polonium. Mass number will drop by 4 down to 218. Polonium 218. Any questions? Sometimes on your exam, I will have an equation like this to balance. Practice for it. This is our very last tutorial. Nuclear equations. What you have are 3 little boxes. I could not get the subscript here in front, just didn't work. So anyway, we have 3 little boxes. Just pretend that this is in front. Magnesium is going to lose something, going to lose an alpha particle. When it does, the mass number will drop from 26 by 4 down to 22. The atomic number will drop by 2, so this is going to be 10. And then if we look at our periodic table, what's 10? Well, 10 is, see, starting at magnesium, go down to 10, that's neon. There we go. So they're fairly straightforward. It's just decent little practice. All right. Quite obviously, as we undergo nuclear decay, we generate new elements. Let's just follow along with our friend uranium and see what happens. This is a radioactive decay table. Diagonals are alpha decay. They go over 4 mass units down to atomic units. Beta particles go up, that's increasing the atomic number. So, uranium is going to be here. Let's start with uranium-238. Uranium-238 loses an alpha particle to give thorium. Thorium loses a beta to give proactinium. Proactinium reforms uranium-234, which loses an alpha to give thorium again. That forms radium-226, and finally winds up here at radon-222. So as these things decay, you get lots of different elements and particles being emitted. Now you may have heard of radon. Radon is a naturally occurring radioactive substance, and it's a gas. That's problematic because it is an alpha emitter. If you inhale enough of the gas, you can get sick and die. Don't want to do that. Well, houses typically are made of concrete, can be made of concrete, but they certainly have a foundation. I have a 150-year-old house with huge rocks as a foundation. But these rocks contain small amounts of uranium-238. Small amounts. That means that the rock will very slowly release radon gas. Okay. Well, granite and stuff like that does contain uranium in very small amounts. And uranium is a very pricey material. Therefore, a lot of rocks are pounded up, extracted, and turned into uranium. But that leaves most of the rock behind. Okay? So you wind up in a uranium mine with these huge mounds of mine tailings, they're called. Little tiny bits of gravel. What do you do with those? Well, you make cinder blocks, that's what. All right, so these are made out of the mine tailings. They have a little bit of uranium left in them. And unlike the big rocks at my house, this is very porous. And the gas just kind of pours out. So, if you're trying to sell your home these days, you have to have it checked for radon, don't you?
That's right.
You put a little detector in there, depending on the reading, You might have to put a fan or something, ventilation in your nice warm basement, dry and cold air, whatever. Yeah, UIC is totally made of cinder blocks, unsealed. I could take my Geiger counter and hold it to the wall and get a reading. Yep, in my office.
Makes sense for the concept. Nah, it's crazy. That makes sense though.
Triton is also made from cinder block, just so you know. But at least it's sealed up behind plaster. So, all right, how long does this transformation take to go from, say, uranium down to thorium? We measure that with something called a half-life. If you start off with 100% uranium and you wait until half of it decays to thorium, the time that it takes to do that is called a half-life. Half-lives follow an exponential decay, never, ever, ever making it all the way to zero. Okay. An example, strontium-90 decays, losing a beta particle to form yttrium, half-life of about 29 years. So after 29 years, half of it has been converted to yttrium. Now, strontium is interesting. Find it on the periodic table. It's right underneath calcium. In fact, it's isoelectronic with calcium. Any place that a calcium will fit, so will a strontium. Now think about bones and teeth. Okay. Well, there was a day when people were developing, learning how to make atomic bombs, and as they put them together, they would set them off in like a desert or some little island in the Pacific or whatever. Well, the infamous mushroom cloud goes way up, gets up in the stratosphere, travels around the world, slowly dribbles down in what's called fallout. One of the things that falls out of this is strontium, strontium-90. So, imagine lush pasture land, and it rains. Strontium-90 washes down, is absorbed by the grass, cows eat it. Children in the 50s, of course, were told, drink your milk, strong bones, healthy bodies. Also, you wind up with strontium-90 50 times above normal in your teeth and your bones. Teeth are just easier to assay. Now, fortunately for all of us that were around in the 50s and early 60s, the half-life is only 29 years. So that means that by now, we're down here, still some, but not life-threatening anymore. Yeah, those were ugly days. All right, half-lives vary. These are like up in a billion years. These are microseconds. So they vary widely depending upon how unstable your nucleus is. In general, the shorter the half-life, the more powerful the radiation for ionizing radiation purposes. Like I said, uranium, 4.5 billion years. Going down to plutonium. Now, plutonium is everybody's choice to make bombs these days, but it's a fairly powerful part of it. There are like 5,000 or 6,000 tons of plutonium in the world right now, in bombs. There's strontium, polonium, very short alpha particle, very, very toxic.
Yes.
And finally, iodine-131. Now this is a beta emitter. This is interesting and or important because we saw the picture of the Japanese power plant that melted down. Well, the same thing happened here in 1976. I-131 is released when that happens in huge clouds. The fortunate thing is the half-life is only about 8 days. 3 Mile Island was where it was released, again in 1979. This was a really bad thing. The reactor floor was breached. It went down, lots of radioactivity poured out, and big clouds of iodine. This is the most toxic thing that came out. Fortunately, there's an easy workaround. Because the half-life is so short, you just take potassium iodide. That floods your body with iodine. You will not absorb it from the air or the clouds or whatever. Do this for a few days and you're pretty good.
I have a question, crazy question. I got an answer. People who are diagnosed radioactive, like who died, where are they buried? Where are they
That's a
buried?
good
Because
question.
it lasts a long time. So
It
where are they
does.
buried?
Well,
Burying
it doesn't, not good for you, that's all.
It's what?
It's just not good for you.
No, I get that.
But do they,
The people who come out radioactive, that died of radioactiveness,
Yeah.
where are they buried? Because they can't be buried in the same
Oh.
cemetery.
You know, I don't know.
Wouldn't they be buried in the same?
Because people would come into the cemetery, so where are they buried?
Besides,
Yeah, I don't know. I've never
Specifically the
thought about
spies.
that.
I'm just saying, I'm gonna get some money.
well, you're, I mean, if they're in a casket, the casket also is sealed with another.
That's
And
right.
that's
They're
the match,
chemical
but I don't know.
You know, bodies are inside of things.
Two
inside of
things, yeah.
They're buried in lead line
Yeah.
coffins.
Yeah,
That's it.
that's what it says.
Just lead line coffins.
All right. Anyway, you're best off to avoid these. Everything from plutonium down, please avoid it. Speaking of, when I came to Triton about 12 years ago, I was going to do a radioactive lecture, and I was digging around in the stockroom, and I found a little box on the top shelf that said radioactive samples. Now, I thought, those aren't supposed to be up there on the top shelf, are they? No. But okay, so I took the box down, and inside of it there was a sample of cobalt-60. Cobalt-60 is a very powerful beta emitter that is used in radioactive medicine. So, the half-life of cobalt-60 is about 5.5 years. Now, I found this like 50 years later. So, when I found it, it was down to roughly 1 or 10, had gone through 10 half-lives. And there was nothing left. My little guidance counter couldn't pick it up. So we're all safe. And I threw it away. And a proper disposal. All right, so here's a problem. Cobalt 65 years, after 15.9 years, how much is left? Well, this is the equation. Believe me, I am not about to try to show you how to do this on your calculator, nor do I expect you to. Let's just do it intuitively. 15.9 just happens to be 3 times 5.3. right? After one half-life, if we started with 1 milligram, we would have half a milligram. After 2 half-lives, 0.25 milligrams. 3, we're down to 0.13. After 10 half-lives, which is what this was, 0.001 milligrams. So again, pretty much not there anymore. All right. In the upper atmosphere, there's nitrogen. The sun spits neutrons at us constantly. Some of these neutrons will hit the nucleus of a nitrogen atom. When they do, occasionally the neutron will stick in the nucleus. That means we make nitrogen 15. Okay, still nitrogen, now it just has 1 extra neutron. Well, it turns out that this is a very, very unstable nucleus. And essentially, as fast as it forms, it breaks down, spits out a proton, and forms carbon-14. Carbon-14 is eventually assimilated into CO2. Okay. This is an example of what's called neutron capture. We'll see that again. But all right. Carbon-14 also decays with a half-life of 5,700 years, loses a beta, and reforms nitrogen-14, completing the cycle of life. Well, this half-life is useful because it's just in the nice available block. Let's pretend that you're alive. If you're alive and you're breathing, you're inhaling CO2, right?
Yeah, we don't inhale CO2.
Some of that's, well, yeah,
Yeah,
every
you do.
time you
Well, I
take a
guess we do,
breath.
but like, not.
And you also eat things that are carbon-based. As you're living and breathing and eating and whatever, you are acquiring carbon-14 and also carbon-12. But the ratio of the two is going to be constant. Okay? Now pretend that you're not living anymore. You're not breathing or eating. So what happens is the ratio of 12 to 14 starts to change. So pretend that you're a saber-toothed tiger. You die, you have a ratio based on the atmosphere. After half-life, you got half as much. 2 half-lives, 3 half-lives. You can take us out with today's instrumentation very far, actually. And you can get very accurate carbon-14 dating data. Kind of a neat technique for half-lives. Any questions? All right. Remember I said beta particles come from neutrons, right? That was strange. Even stranger, I think, positrons come from a proton. A proton can actually lose its positive charge and form a neutron. This is a positive electron. Yes, it is antimatter. It's a positive electron. We're going to take a proton. We're going to lose its positive charge as a positive electron, converting the proton into a neutron and this positron thing. Because we have taken a proton, converted it to a neutron, atomic number decreases by 1, but the mass number is constant. So, this proton will shed its positive charge as the positive electron and reform a neutron. Carbon-11 does this. Here's the positron. Again, this is +1 because it's +1, and we're forming boron. So the number of protons in the nucleus drops by 1. Now, positrons, like I said, are antimatter. If you ever watched Star Trek, Scotty also said, don't let the matter and antimatter mix, because that would be a bad thing. Whenever matter and antimatter combine, you get total annihilation. You form gamma particles. So, here's our positron. It flies until it hits an electron, so antimatter, matter, and it forms 2 high-energy gamma particles. But it doesn't just form these. They're actually released at 90-degree angle or 180-degree angles to each other from wherever the electron was. So they come straight out. Okay? This is the essence of positron emission tomography, a PET scan. Everyone knows some of us had a PET scan. Basically, this is a ring of little Geiger counters. This is a person. What you do is you take a positron emitter, something like fluorine 18. You incorporate it in a sugar. Tumors love sugar. Okay, so this will concentrate at the point of the tumor. Now, as it does, the fluorine will break down to a positron that will hit the closest electron, and we will get gamma rays being emitted directly opposite to each other, like that. So here's my tumor. I get 2 gamma rays coming out, and they're detected. Happens again. Happens again. Happens billions of times. The computer inhales all the geometries here and comes up with a picture of your tumor. This is a PET scan of somebody with an abdominal tumor. Really bad, I'm sorry. But again, the positron hits an electron, you get 2 gamma rays, and the computer maps it into an image.
Would a patient being a diabetic that's not under control throw off the reading at all? Since
No.
it's looking for sugars?
No, they don't give you that much.
Okay.
Doesn't take much. All right, let's go ahead and look at a set of positron problems, both going this way and going this way. Arsenic 70 will emit a positron. The atomic number will decrease by 1 as the proton went to a neutron, but the mass number will stay the same. We're starting at 33, that's arsenic. Let's see, there's 33. We are going to lose 1 atomic number. That's down to germanium. Our germanium would have 70 as the mass number, and 32 is the atomic number. Krypton 77 can lose a positron. When it does, it'll form an element with 35 protons. So we're here, 35 protons, that would be bromine. Mass number won't change. Bromine 77. The question here is what loses a positron to form bromine 79? Well, we kind of just did that. The atomic number will be 36. And again, 36 is still krypton. Krypton 79. And finally, something loses a positron, forms iron 58. The mass number hasn't changed, so this will be 58. This plus this is 27. 27 is cobalt. This is cobalt 58. Any questions? Another way to test on nuclear equations, these are just kind of mixed up. These two are losing betas. We don't know what our particle is here. This guy loses an alpha. See if you can jot through these quickly, if you can see the periodic table. Number of protons will go up to 18. Mass number won't change. We're starting here with chlorine, making it into argon. Argon 39. Again, we're losing a beta. Mass number doesn't change. We'll wind up with 11 protons here. So neon, 11 will be sodium. What has happened here? We lost 2 atomic numbers, 4 mass units. That's an alpha particle, isn't it? Nobelium to fermium, losing an alpha. And finally, plutonium-239 loses an alpha particle. We're going from 92 down to, 94 to 92. Plutonium, there it is, going down to 92. That's uranium-235. Why are some elements radioactive and some are not? Comes down to what's called the line of stability. See the little black line in the middle? These are stable elements. Things that are in blue, these guys emit betas. These guys are positron emitters. And up here, we get fission. Fission is when the nucleus totally breaks apart. Okay. Again, neutron to proton ratio is what determines it. Okay, we talked about making carbon-14 by neutron capture. I just said that heavy nuclei can undergo neutron capture and then fission. This is what makes atomic bombs. Very simple. When typically a heavy nucleus captures a neutron, the nucleus becomes very unstable. One of the most important elements with this tendency is uranium-235. If a neutron is flying about with sufficient energy, it can hit the nucleus of a uranium-235. When it does, this happens. Here's our nucleus. Here's our neutron. It splits open. Typically, there are 3 high-energy neutrons that are released when this happens, plus a lot of energy. About 200 million electron volts for every fission event. That's like 2 trillion degrees Kelvin. It's a lot. For every fission event. These 3 neutrons are released during the fission process. When they do, if these guys just happen to fly on and hit another uranium, you get what's called a nuclear chain reaction. So 1 neutron starts it, generates 3. These generate 9. The next generate 9 times 3, 27. Whatever. Classically, this is shown using ping pong balls. You take a sealed container here with a hole in the top. Each of these mouse traps has 3 ping pong balls balanced on it. This is the 1 neutron that's absorbed. It does this, and whoosh. That's fission. That's the nuclear chain reaction. Once again, uranium-235 to 236 splits open 3 high-energy neutrons. But this doesn't have to result in fission or an explosion anyway, because these have to be absorbed by another 235. That means you need a critical mass. That's what it's for. If you have a small lump of uranium-235, set off a reaction, you'll get some fission, but all these neutrons will escape. That's no good. But if you have lots of stuff, the probability of these all being captured goes way up. That's called a critical mass. Again, doing a video with ping pong balls and mouse traps. This represents a critical mass. Very dense population. The reaction just goes. But if we have a subcritical mass, very low density, like this is an amazing part. Somehow they managed to bounce that little ball without hitting any of them. I wonder how many times we had to do it. But okay, so this represents subcritical, the other represents critical. In a power plant, you don't want it to explode. So what you do is you have control rods. These absorb the excess neutrons. So you stick them down, it shuts the reaction down. You pull them up, and it goes faster. However, if you're making bombs, you don't care about this, do you? You just want it to be an uncontrolled fission reaction. This is a howitzer. These are a bunch of army guys in the 50s. In this howitzer is an atomic bomb with a yield of 1 kiloton. Goes down range 3 or 4 miles. First thing that's going to happen is the shock wave is going to come. Then comes the blast wave, very hot. Here's all the debris, all the dust and stuff. Is simply sucked up into the plastic mushroom. And while this is happening, these guys are just standing here with no protection whatsoever, filming it. Now this particular device was very sophisticated. Again, it's 1,000 tons of TNT. And it's in a howitzer shell. These are the guys that designed it. You can tell it's authentic. So you pull them over, pocket protectors, whatever. Clearly from the 50s. But this is it. Little tiny thing with this fabulous yield for something that small. Well, this was 1 kiloton. The first bomb that was ever dropped was 13, so 13 times that. And it was so simple to make. All you need is uranium-235. Enough to make a critical mass. Called a gun-type fission bomb. This was the first. Basically, you have a sleeve with a hole in it. That's half a critical mass. Here's the other half. This is a barrel. And there's the charge. You fire the charge, the sleeve moves down, you now have a critical mass. Within a microsecond, this is what happens. This is the first one. It was about 10 kilotons.
We're trying to sell.
Uh-uh.
this is sort of serious because it's so simple.
Oh
All you have to do is take 2 chunks of uranium-235, hold them together for a microsecond. That's it.
So,
That's why we worry so much when nations we don't care for make uranium-235, because this bomb is just so simple. Fortunately, nobody makes bombs like that anymore. It uses too much uranium. This is what they make now. It's called an implosion bomb. You start off with a subcritical mass, usually of plutonium. You surround this with explosives. The trick is you have to set all of these off at exactly the same time. Exactly. When that happens, you get a shock wave coming in, the lump of fissile material in the middle is compressed. Its density goes up, its critical mass, and it explodes. But the timing here is just so incredibly difficult to achieve. But the other one's easy. Just eat a lot of stuff. This is the explosive shell. It's about the size of a soccer ball. Each of these are little individual segments that all go off at exactly the same time. This is a plutonium pit. You can hold a plutonium pit in your hand if you want to. It's heavy, but you can. If you put the pit inside the hole here, close it up, you have a bomb. But if you keep this on one shelf and this on another, it doesn't count as a bomb. We have, by treaty, we're limited to so many thousand warheads, right? But we have a shelf with 25,000 of these, and a shelf with 25,000 of these, and all you have to do is put them together. Loophole. Well, implosion bombs, like I said, can be very small. This is one designed to be in a backpack. Army device. Put this on some guy. He's supposed to crawl out of the trench, go to the other side, leave his backpack behind, run back, and it goes off. Well, this is relatively large. This is not. This fits in a briefcase. Yeah, fits in a briefcase. This is actually a Russian device. When the Soviet Union collapsed, the guards left the places where these were stored, and people helped themselves. Nice. There are 50 to 100 missing. Yeah. Well, okay, this is fission. Fission bombs during their heyday went up to like 100, 150 kilotons. This is 100 times bigger than Hiroshima, right? This is going to be nuclear fusion. Fusion bombs are much bigger. If you take deuterium and tritium and you squeeze these together very tightly, it will form a helium, release a neutron, very high energy neutron, and they generate a huge amount of heat. This is nuclear fusion. This is what runs the sun. The sun takes hydrogen, squeezes it together to make deuterium, then tritium, squeezes these together to make helium. That equation, hydrogen to helium, and lots of energy along the way. This is a diagram of a simple fusion bomb. It has a trigger, has deuterium and tritium in here, and uranium too. Does this look familiar? That's an implosion fission device. That's what's used as a detonator. The little firecracker. This is the detonator for a fusion bomb. The very first one, we destroyed some perfectly happy little island in the Pacific, 10 to 12 megatons. The race was on. The Russians managed to get the plans. They made a bomb that was actually supposed to be 100 megatons. But they had to dial it down to 50 because they had no plane that could drop it and get far enough away. This is the Tsar. It's the most fabulous explosion you'll ever see. 50 million tons of TNT. This is Siberia. You're 50 miles away. This mushroom cloud went up 40 miles. All right, why did Russia want a 50 megaton bomb? Well, because they could make bombs, but their guidance on the rockets was so bad. They had no idea where they were going. But if the bomb is big enough, it doesn't matter, does it? This is Lakeshore Drive. There's a field museum. These are Nike Interceptor missiles. Interceptor missiles, yes. Each of these was topped with a kiloton nuclear weapon. The idea was, these are all the bases surrounding the lake here. When the word came that there was one of these missiles coming in from across the pole, everybody would start shooting. Because our guidance wasn't great either, but we started shooting. And hopefully, one of these would get close enough to neutralize the weapon coming in. Burnham Harbor, it's Montrose. Again, nice Sunday afternoon stroll down by the missile battery.
Do you still have them?
Well, they still have interceptors. They're not on Lakeshore anymore. All right, well, that's the bad side of nuclear fission. This is a nuclear power plant, sort of the good side. Most people think that this is the reactor. It's not. It's just a cooling tower. The little round building here is where the reactor actually is. This is Zion, so up north. It's very simple, really. You have pellets of uranium-235. They're in the core. If you want more energy, you pull control rods up, and it runs faster. Push control rods down to slow it down. You take water, circulate it, gets very hot. Goes through one heat exchanger, then through a turbine, through another heat exchanger, and finally is cooled and recycled. What could possibly go wrong? Well, if you can't get the control rods down fast enough, or if something happens to the mechanism pushing them up and down, this just gets really hot, melts, eats through the floor, and we have 3 Mile Island. We also have pumps here. Pumps can malfunction. If you don't pump the water fast enough, well, that's a bad thing too. In Japan, this is again the reactor in Japan. What happened was the earthquake and the tidal wave damaged the reactor building, control rods wouldn't work, all the pumps were out. And it just burned. Today, Fukushima looks like this. It's underwater still. This is very radioactive water. These are the nuclear assemblies called piles. The fact that it's underwater, though, is a good thing. I'm a great fan of water, you know. Water is a remarkable substance. In a working plant, when you're done with the rods here, you have to put them somewhere. Where do you put them? You build a big swimming pool, and you stack up all your used fissile material. Again, this is the reaction we're seeing. See the eerie glow here? That's because the water is interacting with the neutrons that are released. It forms this Cherenkov radiation. And no, I thought artificial wax real. That's what it looks like. All right. So let's say that we have a reactor. We've been running it for a while. The fuel is getting old. What do you do with it? Well, of course, you're going to build a big swimming pool and put it in there. It's the first thing I would think of. These are the sites all around the country that have these giant swimming pools. This is Illinois. We lead the nation. That's because somebody said, gee, people will pay us if we take their used control rods. And so we have all of these piled up. Numerically, Illinois has 99,290 metric tons. We lead the nation once again. It's nice to be first in something, isn't it? All right, well,
that's probably why.
you know, the government decided maybe having this stuff in giant swimming pools isn't a good idea. Okay? So they looked around, and in Nevada, it turns out that they own a mountain. Yucca Mountain. Lovely little mountain. They said, how about we dig tunnels down underneath? We'll take all the radioactive waste, put it down in these tunnels, it'll be safe forever. Now, the people that did this were not scientists or geologists or even chemists, mostly politicians. Nonetheless, they dug these massive tunnels, put train tracks down there so they could move this stuff 1,000 feet underground, devised massive transport trucks to carry hot samples of radioactive waste. You can see it's hot. And their idea was to stick it underground in Yucca Mountain. Well, if they would have asked a geologist, the geologist might have said something like, why is this mountain there? Why does the mountain exist at all? Well, because tectonic plates collide, one breaks, goes up, over, and we have a mountain. This is where they were planning on putting all the stuff, 1,000 feet underground. But right below that is where the crust is broken. That's also called an earthquake zone. So you're going to store this stuff forever in an earthquake zone. Not only that, but 1,000 feet down below, this is the water supply for Nevada. The ground is broken. You have all the radioactive waste from the country here in an earthquake zone. Well, they never put anything in there. That's good. But it still sits in these swimming pools. This is Morris, Illinois. Again, a huge thing. This water gets hot, of course. They take it, pump it outside into big cooling ponds, then pump it back. Once again, have to worry about pumps, don't you? After it's sat in here for a number of years, you can encase it in concrete like this. If there's enough room in between them all, they're hot. You just don't get close to them. Or you could just take it out in the pasture and just kind of dump it. Whatever. So the real problem with fission power is the waste. But fusion power has no waste. The idea is, if we could run the sun's reaction or something like it, capture all this energy, helium is the only product. Once again, just like in a bomb, we would use deuterium and tritium and make helium plus neutrons. So they devised this thing, built it in the 70s. Those are people. This is huge, absolutely huge, very complicated. The idea here is that you're going to take giant magnets. You're going to heat up a gas so it comes to a plasma. That's a charged gas. The magnet will focus this into a tiny little bundle. As you increase the magnetism, the bundle gets closer and closer and closer, and at a magic point, you get fusion. Sadly, it's never worked. Never worked. All the energy that they put in is more than they ever get out. But the idea was simple. Here's your little plasma generator. Fusion reaction occurs. Again, you just pump liquid around, exchange it, and you make power. Just like an atomic power plant, just like a coal plant. You can have coal doing the same thing. I said it hasn't worked, but actually some of the versions have. Just a couple months ago, this guy worked, got more energy out than you put in. These are lasers, very powerful lasers. They focus on a little pellet of fuel here in the middle, all fire at once, compresses, we get fusion, you get energy. Problem is that these lasers are like good for 2 or 3 shots and that's it. So it still has problems. The real promising one are these guys. This is about 3 feet across. This is made by Lockheed Martin at their top secret facility called Skunk Works. And this is a fusion reactor. And it's small, but this is going to work. It really is. MIT has one too. Again, these are people, this is it. These things are small. They do fusion on a small scale, but nonetheless, they work. The idea is you can fit one of these on the back of a truck, or in an airplane, or put it on the moon, or Mars, and it will generate, in this case, about 100 megawatts. That's enough to power a small Midwestern city. But again, they're small. So this is promising. This is going to work one of these days. Any questions? Told you it's a fun chapter.
So, I got a theory, right? So, you know how to get sinkholes. There are sinkholes in the earth, right? You don't know how far, and you know it goes very deep. Why can't they just put radioactive stuff in those things instead of putting it in places where
After Yucca Mountain, I don't think anybody wants to do that. You know, just trying to bury the stuff, putting it in deep wells, stuff like that, no.
So I've heard in the ocean as well.
One thing that I was kind of questioning is one of the photos you showed, it's, we encapsulate the waste into concrete, but there are some radioactive particles of the uranium or whatnot, but so we don't run any risk of that decaying over time?
Of course.
We do. Okay,
Of course you do.
So it's still not perfect.
Look at the expressways, okay? You build them, 20 years later, you build them again. All right. Here's our list. We added a couple of equations today. This is it. Chapter 12 has none. Wednesday, Chapter 12 and 204. Quiz 2, I will put online as soon as I can. Following Monday, Exam 2 review, right here. Print the sample exam, hand one in, 10 points. Exam is the following Wednesday. This is in 204. The magic number here is 350. You must, even if you have more than 350 now, and some of you do, I am so proud of you. You must take exam 2. If your total is 350 or more, you get an A, no final. Work on it, guys. All right, thank you. Have a good day.
There's medicine you forgot to mention. Okay, so
What's that?
radioactive medicine.